In this channel, we have already talked about operational amplifiers. They are great allies in analog design, but despite having already done datasheet analysis, in this video we will give an interesting twist. We are going to learn what not to do with our amplifiers. So, here we are going to push the established parameters for a general purpose BGT architecture, the LM358, to the limit. Let's look at the following parameters. As the first parameter, we have the maximum input voltage. Now, here we could directly interpret that our only limit is the power supply, but we have another detail in question. We also have the case of maximum voltage at the inputs, meaning the non-inverting and inverting inputs. The limit for the inputs is directly determined by the power supply. If we have a 12-volt power supply, our maximum voltage at the inputs will be the same. So let's check these parameters on the oscilloscope. So here we are testing the maximum voltage input of the supply. We have 32 volts and we're going to increase it. We can see the output signal is going to be increasing in amplitude because of the maximum input we have. But after we reach around 55 volts, it is going to stop working properly. We can see the output has dropped drastically. It shouldn't be like this. It should be close to the power supply, let's say, but it is not working properly. So we have damaged the OPAMP. We have went back to the safe value, which is 32 volts, and the OPAMP is not working properly anymore, so we have damaged the OPAMP. So don't increase the supply more than it is indicated. Now we are going to test the maximum input voltage on the differential inputs. So above we have the output signal, below we have the input signal. We are going to increase the voltage of the input signal to see what happens, and we have a power supply of 5 volts. So let's see what happens. We're going to increase it, and we can see we are reaching the floor of the amplitude, so it is behaving like it should not be. So this is what happens when we don't respect the maximum input voltage. We decrease the value and then we reach again a proper functionality of the OPAMP. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In Prisma Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. Operational amplifiers have a bandwidth parameter, which is the maximum frequency at which the amplifier can operate. However, even if the operational amplifier indicates a bandwidth of 1 MHz, it does not really mean that we can use this amplifier at that frequency. What values influence this case? The gain. Now we are going to test gain versus bandwidth. This OPAMP has a relatively low bandwidth, so we're going to see issues quite right away. Here we have 10 kHz. Above we have the output signal, below we have the input signal. We have a square wave, and we're going to increase the frequency. We have other things at hand, which is like slew rate and other stuff, but we can see how increasing the frequency alters not only the shape of the waveform, but also the gain or the amplitude of the waveform. So we have to keep this greatly in mind when implementing our OPAMPS. Let's increase again the frequency. 70 kHz, 100 kHz, 150. Go back again, we restore the output amplitude of the signal. Let's raise it again. We can see the slew rate at hand in this case. Let's increase the gain, and we face the same issue. Let's increase it even more, but we are obviously having waveform issues. So if we need a higher frequency, we need to select a higher frequency op-amp. That's how it is. The slew rate in OPAMPS affects us in many ways, but here we're going to look at it specifically with a square wave signal, where we can best appreciate it. In many cases, we will need to amplify square wave signals, whether for PWM or other types of digital signals. The slew rate then affects the waveform of the signal, which can be even more problematic at high frequencies. Let's look at a direct case. Now we're going to test the slew rate. Above we have the output signal, below we have the input signal. We have a frequency of 1 kHz, and we already can see the rising edge time difference of both signals. Let's increase the frequency. Now we're at 10 kHz, and we can see the rising and falling edges are taking more time to develop. Let's measure them. It is taking 8 microseconds approximately. Let's increase the frequency even more. And we can see that the rising and falling edges are taking way too long. So here we can definitely see how it becomes an issue. And we are at 40 kHz. So we're not even touching the high frequency spectrum. Another aspect of amplifiers that we must consider is the issue of output current. Operational amplifiers do not usually have high current levels, typically below 100 milliamps per output. Therefore, we must take this into account when implementing an amplifier. What can happen if we don't respect this value? Let's see it in the test. So now we are going to test the maximum output current of the op-amp. We have the amplitude on the oscilloscope. We have the current measured on the multimeter, and we can see when we place a load higher than it is specified on the op-amp, which is 30 milliamps, it is going to drop the output voltage because the op-amp has a protection to avoid short circuits. So when a load is higher than it is specified as the maximum output, it is going to protect itself with this measurement or this short circuit protection. So it's not easy to burn the output of an op-amp, but it is possible. So avoid connecting high loads. We can see how if we put a 21 milliamp load, the output voltage drops quite dramatically because we have a high output resistance. So beware of this. If you need to control higher loads, use transistors, use other methods. Op-amps are not meant to control loads. Operational amplifiers, like any other semiconductor, have a voltage drop at their output. This value will vary depending on the consumption current, but it is usually between 0.7 volts and 1.8 volts depending on the amplifier model. How does this affect us? We must consider this when designing amplification stages. If our application requires an output that is very close to the supplied amplitude, we'll have problems. Therefore, the power supply ideally should be 1 or 2 volts above the maximum amplitude we want. Let's see this case in the test. So here we're going to do a simple measurement on the maximum output amplitude. We have an 18.98 volts power supply, and we are measuring how our amplitude goes, which is 17.6. So we have a 1.2 volt drop from the supply to the maximum output. As the last parameter, we have the power supply polarity. As with most semiconductors, we must respect the power supply polarity, since the internal design is already structured to operate in that polarity. What happens if we do not respect this polarity? Let's see in the test. So now we're going to see what happens when we switch the polarity of the supply. We can see that the output current consumption goes to 1 amp. Let's increase the limit. And let's wait to see what happens. And the magic smoke comes out of the op-amp. So we are basically burning the op-amp. It is not going to be operating in any way. In the previous cases, we can see that we could make the op-amp operating in the higher parameters or overloading the parameters, but when it comes to switching the polarity of the supply, it is an instant KO. So be extremely careful with this. Well, we have now seen the most common parameters in which we can make mistakes when implementing an operational amplifier. Like the rest of the components, we must adhere to the characteristics provided by the manufacturer in the datasheet to get the desired performance from the op-amp.